our three organizers for organizing the stochastic computation and complexity at MCQMC 2020. I'm glad to discuss the implicit numerical scheme and the convergence for the stiff differential equation driven by the rough signal today. This is a joint work with Rafael Cruz and Sebastian Riddle. So what is a stiff equation? There are no specific definition for it. In our case, a stiff equation is some kind of differential equation such that if we are going to use certain numerical method for solving it, then the numerical solutions are unstable, unless the step size is taken to be extremely small. So let's look at a linear decay problem borrowed from Wikipedia page. Consider the ODE with a negative constant drift and given the initial condition. We can easily write down the solution. And the solution converges to 0 when t tends to infinity. It is so simple, but some numerical method cannot achieve the same long-term behavior when the step size is not small enough. This figure illustrates the numerical issues for various numerical methods applied on the equation. But let's focus on Euler method only. This red line represents the trajectory from Euler method with step size 1/4, but it oscillates widely and will diverge as time passes by. Then we look at the green one. The green line is a simulation from Euler method with step size 1/8. It oscillates about 0, but doesn't seem to converge. Apparently, with large step sizes, simple Euler scheme doesn't converge. To explore the reason behind it, one may need to write down the Euler formulation. Assume we fix our step size to be h, then the Euler scheme is to evaluate the future evaluation at time tj plus 1 through the current evaluation and its value in the drift. This sort of Euler scheme is also named as explicit Euler because we have the absolute formula for yj plus 1. Now we have a relation between yj plus 1 and yj. Iteratively, we can write down the relation between yj plus 1 and y0. So you can see we have a common ratio, but we cannot guarantee this common ratio is within -1 and 1. Then y is possible to explode when j tends to infinity. For instance, taking h to be 1/4. Here we have some common ratio that is less than -1. Then when j tends to infinity, our numerical solution will jump between positive infinity and negative infinity. So the key point here is a common ratio, 1/15 times h. If we can make it between -1 and 1, then we are safe. By simply replacing this yj in the drift evaluation with yj plus 1 on the right hand side, one can get the contraction relation between yj plus 1 and yj. When j tends to infinity, we can see our solution tends to 0. This sort of method is called implicit method because the right hand side containing some variable we are going to solve, so we don't have an explicit formula for yj plus 1 in this case. Implicit method naturally have a numerical stability and can be used for solving stiff equations. Inspired by this deterministic stiff equation, we consider well-posed equation with some stiff conditions. We started from a simple case when the differential equation is driven by an additive noise x. Here we assume the drift b to be one-side Lipschitz continuous with a constant cb, and also locally Lipschitz continuous. This one-side Lipschitz continuity allows speed to grow more than linearly in the negative direction. Besides, this is a natural generalization of the linear decay problem if this CB is smaller than 0. On the other hand, this local Lipschitz continuity is a relaxed condition such that the growth can be characterized locally. From a perspective of dynamic system, those two conditions ensures a contractive dynamics. Under the assumptions on drift B, we can show the solution exists uniquely and enjoy the same continuity property as the driving noise. So for example, if X is of 1 over P holder continuity, then Y is also 1 over P holder continuous. Usually, equation 3 has no closed form, so we sought to find its implicit Euler numerical simulation. To construct such numerical scheme, we fix an equidistant partition for simplicity. This result can be generalized to any time grid. We iteratively evaluate the solution at time tj plus 1 based on equation 4. Here we substitute the unknown yg plus 1 into the drift. To solve it, we group all the unknown terms, that is yg plus 1 and hb yg plus 1, on the left hand side and the rest in the right, and try to find the solution for each step. Now the question is if this equation is solvable. Indeed, the well-posedness can be ensured by applying the so-called uniform monotonicity theorem under some constraints regarding the step size. Indeed, the uniform monotonicity theorem tells us if we have a targeted function which satisfies this inequality, then the target function has a continuous inverse, which is Lipschitz. For our case, we define G to be the unknown terms. Then we can check the inequality holds because of the one-side Lipschitz continuity. Therefore, the map is invertible, and yg plus 1 can be solved by inverting G. The second issue we need to deal with is the boundedness of the numerical solution yn. To do it, we need to first change variables. So here we define a new variable un as a difference between the solution yn and the noise xn. Then the implicit Euler scheme can be reformulated in terms of un and xn. Instead of showing the boundedness of yn, we show the boundedness of un. To achieve this, we estimate some quadratic quantity of uj. This quantity has very nice properties such that it can be written in terms of inner product of uj and uj plus 1. Then we can make use of one-side Lipschitz condition to get the upper bound of equation 5. Then we sum both sides up to n to get equation 6. You can see on the right hand side we have some consolation and some positive sum that can be ignored. Afterwards, we can apply the discrete ground wire inequality to show the boundedness of un. For the convergence, we consider two cases: when the driving noise is of finite p variation, and when the driving noise is of 1 over p holder continuity. For both of the cases, the order of convergence can be 1 over p. This has been proven as the best order of convergence with any deterministic scheme. When p is quite large, equivalently when the driving noise is very irregular, we may not have a scheme that gives satisfactory convergence. One way to improve the convergence is to incorporate the stratified Monte Carlo method into the scheme. Cruz and I developed the so-called randomized numerical scheme in 2017 for the drift being Lipschitz continuous. Those schemes include randomized Euler scheme, a randomized Rancuda method. Later on, it was extended to the Steve problem. Here we consider the scheme after changing variables. In each of the evaluation, a uniform distributed time variable is introduced here to interact with our driving noise x. Then the order of convergence can be lifted to be at least half, even if the driving signal is quite irregular. Before proceeding to the multiplicative noise case, let's show you one numerical example. This is a scalar rough differential equation with a driving noise smoother than Brownian motion. It is easy to check. The drift is not only one-sided Lipschitz but also Lipschitz. However, the numerical solution from explicit Euler on a coarser grid is divergent, while the implicit Euler convergence as expected. This is just an illustrative example. We then consider multiplicative noise case. So here we consider the multiplicative version of differential equation with the driving noise being 1 over p wholly continuous when p is between 2 and 3. However, this kind of equation is ill-posed in general, and we have to use rough path theory to make sense of it. So we studied the lifted differential equation 10, where the enhanced rough path of the driving path x is indeed the signature of the path up to the second level. So this is first level and this is the second level. As p is between 2 and 3, it is enough to truncate the signature to the second level. Here we define 1 over p hold the rough matrix for later use. The assumption on the drift is the same as before. To make sense of our rough integral, we introduce the so-called Gubinelli derivative. So for a rough path x, a path y is said to be controlled by this x if there exists a y prime such that the remainder term given implicitly through this relation is bounded in the holder norm. This y prime is called the Gubinelli derivative of y, though y prime is not uniquely determined from this y. As a consequence of solving lemma, the rough integral exists as the limit of a Riemann sum in terms of the first and the second level of signature of x and the Gubinelli derivative. For our case, we call path y is a solution if for any time it satisfies this rough integration equation. As the main part of analysis is in a language of dynamic system, so we first define what is a semi-flow. So this is a semi-flow. We also assume our differential equation induces a continuous semi-flow. This is not a very restrictive assumption because previous literature has addressed it. The main proof of the numerical analysis rely on a localization argument. For this, we would assume B to be Lipschitz for now. Then we can show that the rough differential equation does induce a continuous flow. Besides, we can show the flow is Lipschitz in space. We now propose an implicit Milstein method to approximate the solution of the RDE. We truncate the Taylor expansion-like series up to the second level of signature and use the future evaluation in the drift only. Indeed, we also consider implicit Euler and the third-order Milstein due to limited time, and will focus on implicit Milstein in this talk. The well-posedness can be solved using the uniform monotonicity theorem as shown before. When our drift is Lipschitz, we can characterize the local error of the implicit Milstein method with order 3 over p. Then, based on a localization argument, we can show the convergence for the implicit method is 3 over p minus 1 if the drift is one-sided Lipschitz. The idea is as follows. I will give you a sketch. So we first find a ball with radius m such that the whole trajectory of the solution is within the ball. Since the drift b is locally Lipschitz continuous, therefore bounded in the ball, then there exists a bounded Lipschitz continuous function b bar here, which coincides with b in the ball. So we can consider a new rough differential equation with Lipschitz condition and define its Milstein solution as y bar n here. From proposition 1, one can show the new RDE induce a semi-flow, phi bar. And from proposition 2, we can show the order of convergence of the new RDE is 3 over p minus 1. Note that phi bar and phi coincide within the ball. Then one can choose a sufficiently small delta such that the numerical scheme for the new RDE is within the ball too. Finally, applying the uniqueness of the uniform monotonicity theorem, we can show y bar coincide with y tilde, which is the implicit Milstein method for our original RDE. It is also worth noticing that the last term involves calculation of the second-order iterative integral, which, while in the real life, is very hard to achieve. One alternative way to do it is to replace the second-order term with a simple product of displacements. Here we define the solution as y bar. Y tilde. For the simplified version of implicit method, Milstein method, we further assume our path is Gaussian. Then its enhanced path is almost surely 1 over p whole continuous for any p between 2 row and 3. We then further assume the semi-flow induced is bounded. Then the order of convergence would be with order 3 over p minus 1. The proof is not new but very intuitive. So we first introduce piecewise linear approximation of x denoted by x h and consider the differential equation driven by the canonical lift of xh and define its solution as phi h and its implicit Milstein method solution as y height h. Then we have a very key observation here. This implicit Milstein solution of the newly defined equation, which is y height h, coincides with the simplified implicit Milstein method of RDE of our original RDE, that is y tilde we just defined. Then the error term can be decomposed as two terms. The first one is the von Zake error, and the second one is indeed the convergence for the implicit Milstein method we just shown. Finally, we tested our scheme on equation 15, where the existence of the semi-flow have been shown by redo and pseudo. We choose the driving path to be a two-dimensional fractional Brownian motion with Hertz parameter 5/12, and the drift satisfy our assumption. Yeah, according to the convergence results, the order of convergence should be around 0.25, but you can see in practice, the experimental order of convergence is much larger. The second plot just show you the trajectory from both implicit and explicit scheme. You can see clearly the explicit scheme has a worse performance for simulating the true solution path, though it is not dramatically deviating from the true path as we shown in the Steve problem before. Yeah, thank you for attending my talk. Any questions?